Okay, the carbon cycle. So this is something that seems to have a new focus on the syllabus, so we need to dedicate a little bit of time to it. So we've talked about carbon dioxide, we've talked about global warming and the effects of an increase in average temperature of the atmosphere and some of the things that that causes. But let's have a little look in detail at the processes involved in this cycle. The diagram illustrates many of these, and we'll work through them in a second. But what were the sources of carbon dioxide? Okay, the complete and incomplete burning of fossil fuels throws more carbon into the atmosphere, and we're doing that quite a lot, although we're trying to reduce it. Unfortunately, the world needs energy. The world is obsessed, it's an energy junkie, and we need to find ways of making sure that we satisfy those needs that don't damage the planet. So, burning fossil fuels, respiration and flatulence. There's the respiration equation, isn't it? You can write that down. Glucose reacting with oxygen to make carbon dioxide and water, and also industrial processes. The ones we mentioned were carbonates, thermally decomposing, and also reacting with acids. We seem to be upsetting the natural equilibrium of things. How naturally is carbon dioxide removed from the atmosphere? And we're putting lots of it into the atmosphere, but how is it removed? Well, it's removed, as you know, by photosynthesis. Plants use sunlight, chlorophyll, to the energy from the sun and chlorophyll in this photochemical reaction to absorb carbon dioxide with water to make glucose and oxygen. Okay, so we'll start here. Look, photosynthesis is here. Sunlight and photosynthesis, chlorophyll, remove carbon dioxide from the atmosphere, and it's trapped in plants. Those plants can decay to produce more carbon dioxide, but also those plants can also produce organisms, waste products, which can go on to be fossil fuels, can't they? They can go on to be fossil fuels, or they can be eaten by animals, by us. Respiration takes place and carbon dioxide goes back into the atmosphere. When plants respire, they also produce carbon dioxide. Luckily, they produce more oxygen than carbon dioxide. Root respiration obviously produces carbon dioxide. So this is where the carbon goes once it's trapped by the plants. Okay, respiration. There's also, because of the fossil fuels that we've already got, there's also a large amount of carbon dioxide that goes into the atmosphere through the burning of fossil fuels and other fuels. You can burn wood as a fuel, which is a natural fuel, and that sends carbon dioxide back into the atmosphere. The last thing to point out is the idea of ocean uptake. The oceans absorb carbon dioxide. Now, this is something that happens better when the oceans are at lower temperatures. So as the temperature of the oceans increases due to global warming, then they can absorb less carbon dioxide. So that again adds to this effect. It's a crazy cycle that we've got ourselves in, and we've got to somehow break it over the next 50 years to a century. Otherwise, doom, or worse. Right, have a look at those pages from Essential Chemistry and answer the questions. Water. So the first thing you need to know is some uses of water. Okay, so I've illustrated some uses here. Uses in the home, uses in farms, industry, and in power stations. So in the home, what do we use water for? Well, there you go. We use it for lots of different reasons, don't we? For washing up and all the other reasons here. Farms, obviously we use it to irrigate the farms so that we can grow crops. Mainly, we also use it to water the animals. In industry, we use it for cooling. And in power stations also, we use it for driving the turbines and for cooling. These are cooling towers. Believe it or not, this isn't smoke, this is water vapor coming out of these towers. So in industry, typically we use water for cooling. We can use it in some chemical processes, but typically we use it for cooling. Nuclear power stations are always next to some large water source so they can cool themselves down. So you need to know some of these uses. So how is the water purified? We take water from relatively clean sources. We don't take it from the sea because it's too salty, although we can desalinate the water from the sea. We take it from rivers, reservoirs, or aquifers. Aquifers are large deposits of water underground and typically are very pure anyway, so can be used often without very much treatment. But what we need to do is make all of this water fit for human consumption. So we must remove essentially two things. The particles, large and microscopic, so things that would make the water cloudy and essentially can give it a little bit of a nasty smell or flavour. And also we need to remove anything that might be dangerous to the human organism, like bacteria and other tiny organisms, so microbes. Okay, that's typically the two processes, the two main things that we do to the water. So let's look at this outline of a water plant. The water comes in, there'll be a screen to stop bicycles and dead dogs going into this. The water's pumped into a coarse filter. This could be a filter through sand to get rid of the big particles. Then it's allowed to undergo sedimentation. Often they add something to cause the microscopic particles to kind of join together, to clump together, and they sediment, they precipitate down to the bottom of the tank. Then it's passed through a fine filter, which often has carbon in it to remove any odours, any smells. Chlorine is added, which kills the bacteria, and then the water's put somewhere to store it until we need it. In Madrid, for example, there's an enormous place in the centre of Madrid which is an underground storage tank. You might have come across that. They've built a golfing range, a driving range on top of it, and a park. But there's an enormous, enormous tank underground for the water of Madrid. Okay? The water doesn't have to be disinfected, chlorinated, if it's destined for other uses. So if it's going to be used to irrigate golf courses or used in industry, some parts of industry will need the particles removed, but not the water to be drinkable. Fluoride sometimes is added to water to reduce tooth decay, but that causes quite a bit of fuss in the population because they see it as mass medication. Right, tests for water. The physical test, obviously, if we've got pure water, then it boils at 100 degrees C and it freezes at 0 degrees C, as you know. Okay? If the water's impure, it would boil at a temperature higher than 100 and it would freeze at a temperature lower than 100 to show there's impurities. Chemical tests. The water or an aqueous solution will cause the following colour changes. So with anhydrous copper 2 sulfate, anhydrous means it's had its water removed. It's white. Here it is here. We've taken the water out of the copper 2 sulfate. If we add water back to it, it goes blue. Okay. This hydrated copper sulfate is blue. This is anhydrous. This .5H2O is the water of crystallization. Okay, so if we've got the anhydrous copper 2 sulfate, which is white, and we add water, then we cause a reaction to go in this direction, which is actually exothermic, but that doesn't matter. It turns blue, and that tells us that we've got water. If we heat the hydrated copper sulfate, then we get anhydrous copper sulfate back. So if we heat the blue copper sulfate, we get the white copper sulfate back. Okay, copper 2 sulfate in each of these cases, obviously. Anhydrous cobalt 2 chloride will turn from blue to pink. You need to know these colors. So if I add water to anhydrous, dry anhydrous cobalt 2 chloride, it will form this salt, cobalt 2 chloride dot 6H2O. That's the hydrated salt. So I start with my anhydrous blue cobalt 2 chloride. That's this. And if I add water, if there's water coming out of this tube, then it turns this blue paper, which has got some cobalt 2 chloride on it, it turns it to pink. And that's a test, a chemical test for water. Right, essential chemistry, read the pages and answer the questions.